Let's continue discussing series. So the next thing we're going to talk about is the divergence test. So remember that the divergence test tells you if the limit of an is not 0 or the limit does not exist, the series diverges. So let's look at an example where we could use the divergence test, determine whether the series n squared minus 1 divided by 4n squared plus 1 converges or diverges. So if I take the limit of the terms n squared minus 1 over 4n squared plus 1, the numerator and denominator have same degree, so it's the ratio of the coefficients, it's 1/4, which is not 0, so this series diverges by the divergence test. And then we also had p-series. P-series were series that look like 1 over n to a power p, and it converges if p is greater than 1, and it diverges if p is less than or equal to 1. We also had the integral test. So the main thing you should remember about the integral test are the conditions on which you can use it. When you turn your series into a function, this function needs to be continuous and positive and decreasing. So an example where I would use the integral test is determine whether the series one over n ln n is convergent or divergent. So the first thing you do if you're going to use the integral test, turn it into a function, swap out n for x. This is continuous because the denominator won't be 0, and positive on my interval 2 to infinity. And now we need to show it's decreasing. You can rewrite the function like this. Use the chain rule to take the derivative here. F prime of x would be x ln x to the -2. And then inside derivative would be the product rule. So you get negative ln x plus 1 over x ln x squared. The denominator is positive because it's a square. The numerator, the inside part in the parentheses will always be positive, so there's this minus sign out in front, which means this is going to be less than 0 on your interval 2 to infinity. If your derivative is less than 0, it means your function is decreasing. So then you compute the integral, the improper integral from 2 to infinity. And this is an improper integral, so you have to put in a limit. And then we would do a substitution here. U be ln x, du is 1 over x. This would be the limit, ln of 2 to ln of t, 1 over u. The integral of 1 over u is ln of u. So then this would be the limit as t goes to infinity, ln of t minus ln of 2. Well, that limit would be infinity. And so the integral diverges, which means the series diverges by the integral test. So my series diverges by the integral test. Okay, and then we also had comparison tests. And there were two different versions of comparison tests. There was the direct comparison test and the limit comparison test. So let's look at an example here. Is the series n equal 1 to infinity, 4 to the n plus 1 over 3 to the n minus 2 converge or diverge? Remember that in order to use a comparison test, your series has to have positive terms. This series, this is always positive. And remember, we have to come up with a bn and we make small changes. So in this case, our bn, the small change I'm going to make is I'm going to get rid of the minus 2 in the denominator. So now I'm looking at 4. This is a geometric series. Our r is 4/3, which is bigger than 1, so it diverges. And then if we're using the direct comparison test, we have to compare to the original, and we have to figure out which one of these is bigger. Well, this one has a smaller denominator, which means a bigger number. So we know that the smaller one diverges, which means this larger one diverges as well. So I can just use the direct comparison test here and say 4 to the n plus 1 over 3 to the n minus 2 diverges by direct comparison test. All right, and our final comparison problem we're going to look at is, I want to know, does this series converge or diverge? The series has positive terms, so you can use a comparison test with it. And so what should we compare with? Compare with, remember, you take the largest degree in the top, n squared, largest degree in the bottom, and simplify 1 over n squared. This is a p-series where p is 2, which is bigger than 1, so it converges. And then I would just go ahead and use a limit comparison test because you changed both the numerator and denominator. So take your an and divide by 1 over n squared, or flip it up. This would be the limit of n to the fourth plus n cubed plus n squared over n to the fourth plus n squared. They have the same degree, so the limit is the ratio of the coefficients. It's 1. And what you need to get here, you need to get a finite number that's non-zero. So we got a finite number and it's not 0, so both of the series have to behave in the same way. So I now know that this series that I was asked about converges by the limit comparison test.